So now we've learned how to break out perfect squares from inside a square root, as well as make it so that there are no fractions under the square root. Kind of. All right, so the problems I gave you here all kind of worked out beautifully. So the denominator disappeared. But that doesn't always happen. And according to the rules of simplification, you're not allowed to leave a square root in the denominator. Okay, so that means that you are going to have to simplify these another way, using something called rationalizing the denominator. It's a little technique, a little trick we use to change what it looks like, but it doesn't change the value of the radical. So I start off here with 4 square root of 7. So what I need to do is I need to change this so that it's not a square root of 7 underneath there anymore. It's a square root of something else that's a perfect square, something from our list of perfect squares. So if we think back to the list of all these numbers, well, the one from our list that was a perfect square is 49, right? So if I can make 49, that 7 goes into, I should say, then we'd be great. So the way I can do that is multiplying by the square root of 7 over the square root of 7. By doing that, I'll turn my numerator into 4 square root of 7, and my denominator will become the square root of 49. But the square root of 49 is 7. So that's 4 square root of 7 over 7, and we're done. Beautiful, isn't it? So you're multiplying by something that'll make the denominator disappear on purpose. You're squaring a square root, and when you square a square root, that makes it go away, right? Because they're inverses of each other. So if you take square root of 7 and you square it by multiplying it by itself, you will get the square root of 7 squared, which automatically will be 7. You get the radicand, is what that's called, 7. All right, so let's do it again. So this is the square root of 2. Oopsie. There we go. Square root of 2 over the square root of 5. So we multiply by square root of 5 over the square root of 5. Why? Well, because 5 times 5 will make 25. It'll be a perfect square. So the numerator is the square root of 10. The denominator is the square root of 25, which is the square root of 10 over 5. Now, in an intermediate class, we don't really show this step all the time. We often just skip over it and jump right to the final result, because you're all expected to know that the square root of 5 times the square root of 5 is 5. It's an inverse property of square roots. Now let's do it for a trickier problem, like the square root of square root of 7 over 12. Okay, so that's negative square root of 7 over the square root of 12. No troubles. But here's where we run into trouble, which is that we need to get rid of 12. 12 is not a perfect square. Well, we could do this a couple ways. Like you could multiply by the square root of 12 over the square root of 12. But the problem with that is that you're going to end up with a very large number in your numerator. You're going to end up with 84, and then 84 has a perfect square. So let me just write it. It's the square root of 84 over square root of 144, and then you got to break it down. You got to say that's negative. Okay, square root of 84 is 4 times 21 over 12. 4, let's see, that becomes 2, so this is negative 2 square root of 21 over 12, and then 2 goes into 12 6 times. So this is negative square root of 21 over 6. It's doable, but it's kind of a pain, right? Okay, so what's another way to do it? Because that was kind of annoying. So let me put this over here. There we go. So that's way number 1. Ugh. All right, so let's do a faster way. Way number 2. Okay, so I could say it was negative square root 7 over 12. We all know that that's negative square root of 7 over square root of 12. It doesn't matter if the negative's out in front or up in the numerator. It doesn't really make any difference. Put it in the front if you like. And think, okay, I'm not going to do 12. 12 left me with this mess. When you did 12, you had to do all the simplifying stuff. Ugh. So what I'm going to do is I'm going to think about 12 just a little bit. 12 is 4 times 3, right? But 4 is already a perfect square. So the real trouble is the 3, the extra 3 that you have there. So if I just multiply by the square root of 3 over the square root of 3, that'll turn that denominator into square root of 36. And 36 is a perfect square, right? So this is negative square root 21 over 6. It's a much faster way. If you don't multiply by everything, you just multiply by the little bit extra you need to make a perfect square. Right? That's a much better way of doing this problem than the other way. So I prefer it. Now, if you don't think of it, that's fine. You can do way number 1. It's just going to take you longer, right? All right, so now let's think about this one. This is the square root of 9 over the square root of 32. That's the square root of 9 over the square root of 32. Well, we know the square root of 9 is 3, so we might as well do that right now. And then let's think about 32. 32 is 16 times 2, right? So 16 is already a perfect square. So what I need is an extra 2, right? Because 2 times 2 will make 4. So what I'm going to do is I'm going to multiply by the square root of 2 over the square root of 2. That'll turn it so that my denominator is a perfect square because it'll be 64. And 64, 32 times 2 is 64. 64 is, the square root of 64 is 8. And there we have it. So I'm using way number 2 in case you missed it. I'm using this faster way. I'm not multiplying by the square root of 32. That would just be huge. What I'm doing is I'm multiplying by just a little bit extra I need to turn the 32 into a perfect square. Okay, now what about square roots of negative numbers? Now a lot of students think that you can take a square root of a negative with the real number system. Like, for example, they'll look at the square root of negative 25 and they'll think, oh, well that must be negative 5. But that is wrong, wrong, wrong. Okay, here's why. What's negative 5 when you square it? So if you take negative 5 and you square it, what you're doing is you're multiplying it by itself. So you take negative 5 times negative 5. But a negative times a negative like that is positive, right? Not negative. So that's not going to work, unlike what most people really want to believe, right? So you can't take the square root of a negative number in the real number system. So back in the day, they invented a new number system called the imaginary number system, wherein the square root of negative 1 is equal to I by definition. They just call it I. That's called the imaginary unit. This was popularized first, it was first discussed by Girolamo Cardano in the 1500s, but it was later popularized by Euler, the same Euler that we learned about in Chapter 5, and Carl Friedrich Gauss, one of the greatest mathematicians of all time. René Descartes is the one that said imaginary because he didn't like it. He's the guy that thought of the x and y axis that you know and love for graphing. So without him, you wouldn't be graphing that way. But he poo-pooed this whole idea and said it's imaginary. He was in French, right? So he didn't really like it very much. Okay, so, but that doesn't mean that it doesn't exist. Electrical circuits all work off of an imaginary solution, right? So if you take any kind of physics class with electrics, they'll talk about it. So they have solutions. They're just not in the real number system. They're not rational. They're not irrational. They're something else. All right, so let's learn how to find some. So let's take the square root of negative 49. This is equal to the square root of negative 1 times the square root of 49. Well, that's I, by definition, times 7. And no mathematician of self-respect would ever write it that way because that's ugly and it requires them to write a dot. And they would never do that because they're lazy. And so they'll write 7i instead. Just like 7x, you write the number in front. So 7 becomes the coefficient. All right, so let's do this again. This is negative square root of negative 1, square root of 81, right? You're breaking up the negative 1 and 81 part. Okay, so that's negative I. Square root of 81 is 9. So a negative I times 9, which is negative 9i. So the negative in the final result came from this negative just to begin with. That negative just sits there every step of the way. And then the negative that was under the square root became the I part. All right, now what about this one? Okay, so my first step is going to be to take the I out and to break up the radical. I'm going to do 2 steps at once. This is going to rock your world. All right, so negative. I'm going to make it I square root of 3 over the square root of 20. Now 20 is not a perfect square, but I could multiply by something to make it turn into a perfect square. So I think to myself, 20 is 4 times 5. 4 is a perfect square. So 5 is the extra part. So if I multiply by the square root of 5 over the square root of 5, that'll get me 100 in that denominator. So let's think. This is negative I square root of 15, because 3 times 5 is 15, over the square root of 100, and the square root of 100 is 10. So it's negative I square root of 15, I square root of 15 over 10. And we're all done. There, I had to press enter to kind of get that to fit. All right, so now what about this one? All right, so the negative part's going to become I. And I'm going to break this up a little bit. So this is I in front, and then I'm going to take a moment and just reduce my fraction. That's 1 over 27, right? Because 2 goes into 54 27 times. So this is I, and I'll just put the I up on top. It doesn't really matter where it goes, but it's the square root of 1 over the square root of 27. But the square root of 1 is just 1, right? So that's no big deal. And then 27. 27 is 9 times 3, 9 being a perfect square. So what I need to do is I need to multiply by the extra part, which is the 3. If I multiply by the square root of 3, I'm going to get 81 in that denominator, which is great because if I have the square root of 81, that'll be a perfect square. And my numerator, that's 1i times the square root of 3, so that's just I square root of 3, right? Because 1 times 3 is 3. So we just need to figure that out. And that is I square root of 3 over 9. And you're done. Okay, so imaginary numbers are of the form bi. These are all the ones you're kind of coming up with here. Matter of fact, I can say it this way. Or, there we have it. So it's the same thing as saying negative square root of 15 over 10, I, and putting the I in the back. Sometimes we don't care about that form particularly, but if you want to write it that way, you can. Then we could say it over here, and then I could write it again. One sec. There we have it. The square root of 3 over 9, I, where you stick the I in the back. That's the true format of imaginary number. And that leads to a whole another set of numbers called the complex numbers, which we're not going to really deal with much here, but they're of the form a plus bi. So you could take like 5 minus 2i. That's an imaginary number. Or, let's think of the one we just had. Where was it? So it was square root of 3 over 9i. So I could say 17 plus the square root of 3 over 9, and then put the I in the back. Oops, I pressed the cap lock button. Sorry about that. Oh, for the love of goodness, turn off the caps lock. There we go. Good grief. All right, then what about, let me think of the other one we did. So we had 82 minus the square root of 15 over 10i. Those are all imaginary numbers, or excuse me, they're complex numbers. Technically, the imaginary numbers are complex numbers on their own. They're just 0 plus 7i. So I could say like 0 plus 7i, but that's the same thing as 7i, right? So imaginary numbers are complex as well. You deal more with that in a pre-calculus class. So I just wanted to touch on it here so you can see what complex numbers look like. All right, so we're done with that section, and then I'll meet you back here for the last part, which is simplifying some pretty ugly looking radical fractions, which are necessary for solving quadratic equations, which is coming later on in Chapter 7. So I'll see you then.